Hello, today we are doing problem 9.56. This problem asks us to explain the following observation. So when we react this first molecule here, being 3-methyl-2-butanol, and when we treat it with HBr, a strong acid, a single alkyl bromide is isolated. Specifically, this is due to the 1,2 carbocation rearrangement and hydride shift. However, when we react 2-methyl, 1-propanol, and we treat it with the same reagent, we don't get any rearrangement, we don't get any carbocation rearrangement, and we still form this alkyl bromide product. But it is asking us, why do we observe a carbocation rearrangement or hydride shift in the first example, but not the second example? So let's go over the mechanism to see why that is. So obviously we have a strong acid, so that dissociates to H plus and Br minus. We have to identify a nucleophile, that's being our alcohol of the oxygen, that can pick up this proton here. So now we have this protonated water, which is not stable, not favorable. Oxygen likes to have negative or positive or neutral charge. So because it has a positive charge, water will spontaneously fall off. Now we have a secondary carbocation. So adjacent to the secondary carbocation, we have this beta proton, which can do something called a hydride shift to form a more stable intermediate. And that leaves us with now a tertiary carbocation, in which point this bromine ion, which is being the nucleophile at this point, can attack with 50% equal probability from the top as from the bottom, giving us a racemic mixture of products. So as you see here, the top example goes through an SN1 mechanism in which we form a carbocation intermediate. And to represent the two products that this bromine ion can represent, either being a top or bottom addition substitution reaction, we can just draw a squiggly line showing that it's both a wedge and a dashed lines, meaning coming out and into the page respectively. However, here, if we see in the second problem, if we pick up that proton and water falls off, what we're left with now, if that were to occur, would be a primary carbocation. So primary carbocations do not form. They are not stabilized and they're not favorable. So this pathway will not occur because, once again, primary carbocations are not formed. They are not stable, it's not favorable. So this water will not spontaneously fall off. Instead, it will just stick around on the molecule until the bromide ion comes around and is able to do an SN2 nucleophilic attack from 180 degrees backside attack, making a new bond. When you make a bond, you break a bond. So that is what kicks off this water. Now this gives us our substitution product plus water. So you see the top example goes through an SN1 mechanism, meaning that a leaving group leaves first. This generates a carbocation intermediate, which can undergo hydride shifts to generate more stable carbocation intermediates, giving us this product that we see in the question stem. However, the second example goes through an SN2 mechanism. So there is no carbocations can be formed, no sort of shifting that is possible. Why? Because if water were to spontaneously fall off before the nucleophile attacks, it would lead to a primary carbocation, which is not stabilized, therefore will not occur. So that is why the nucleophile must attack first to promote kicking off of the water.